So next we will proceed with the introduction to digital electronics, that is basic of digital electronics. So in that, now we will start with the number system. So basically our computers works on different arithmetic and logic operations. So different arithmetic and logic operations are being performed, and that logics are performed on binary numbers. So there are different types of number or different types through which we can represent a number. We are having the different representation of numbers. How we can represent a given number based on our convenience. We can use different methods or different sign conventions through which we can represent a number. So the most frequently used that we use in our daily life is decimal number system. Another one is binary. Next is octal, and next is hexadecimal. These are the four different number systems we will be using in this discussion. Basically, based on these number systems, what we do is we do arithmetic and logical operations. How we will be converting one number system to another number system, we will see that. And also we will see is how we can represent complement method. So we will be performing complement, how we can use complement for representation of negative numbers. So in this lecture we will just see different number systems and how we can convert one number system to another number system, and also we will see how we can represent this negative numbers with the help of complement. So starting with the decimal number system. So before that, we will just see how we can represent a number. So any number, when we go with a representation of number, so in that number we have a base on which a particular number system is represented. So it is having a base, or we also called radix. Like a decimal number system is there. So when we represent like 0, 1, 2, 3, you can also represent it like 0 that is having a base 10, or 1 that is having a base 10, 2 is having a base 10. That means on base 10 this 2 is defined, or a number is there 2, 3, 4 is there. So this is having, it is a decimal number, so we will be representing with in bracket a base subscript will be there, that is 10 will be written. So this 10 represents the base. So how this base is related, we will just see. So here if any number system is there, so for any number system having radix, or we call it base, is having a radix or base r, the different uh, digits possible will be between 0 to r minus 1. That means if any number system is there and it is having a base or a radix, that is r, then that number system will be having different digits, so that digits will be in the range of 0 to r minus 1. So just for an example, if we consider the example of a decimal number system, or suppose a number system is there and its different digits. If we write, suppose the first one is decimal number system. If decimal number system is there and it is having a base or radix, we can just write here radix or base. So in decimal number system, the radix or the base is 10, and if it is having a radix 10, then the total number of digits possible in this decimal number system will be ranging between 0 to r minus 1. R is radix, so it will be ranging between 0 to r minus 1, that means 10 minus 1, that is 9. So the different digits will be 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Another number system, that is binary, it is having a radix. So binary is having radix, that is base, that is 2. So if it is 2, the different possible digits will be ranging between 0 to 2 minus 1, that is 1. That is 0 and 1 will be there. Next one is octal. So in octal number system, the radix is 8 or the base is 8. So if radix is 8, the number of digits possible will be between 0 to 8 minus 1, that is 7. That is 0, 1, 2, 3, 4, 5, 6, and 7. The fourth one is hexadecimal. So hexadecimal is having the radix, that is base of 16. So if it is having a radix or base of 16, so the different possible digits will be between 0 to 16 minus 1, that is 15. Okay, so it is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10, 11 up to 15. Okay, but the numbers ranging between 10 to 15 have been given a different code. Okay, so in case of hexadecimal, so any number that is ranging between 10 to 15 has been given the code like 10 will be represented by A, 11 will be represented by B, 12 will be represented by C, 13 will be represented by D, 14 will be represented by E, and 15 will be represented by F. So it's having the different digits, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then A, B, C, D, E, and F. So this is how the different digits of number system is defined. Suppose we are having a number system, suppose any uh, X number system is there, and it is having the base or radix is suppose 3. So if it is having radix 3, in that case the possible number of digits will be 0, 2, and r minus 1, that is 3 minus 1, that is 2. So it will be 0, 1, and 2. Similarly, any other number system, that is y, having base, that is suppose 12 is there. So 12 is the base. In that case, possible digits will be ranging between 0 to 12 minus 1, that is 11. So that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So if it is 10, it will be represented by A, and 11 is B. Any number system, that is Z, it is having suppose 5. Radix is having 5 or base is having 5. In that case, the number possible digits will be 0, 1, 2, 3, 5 minus 1, that is 4. Up to 4 it will be having. So this is how we can represent any number of digits possible for any number system that is defined with its radix. Its base is known. So what is its base? then we can represent the possible number of digits for that number system. So once we know like how we can represent a number system, that is decimal, binary, octal and hexadecimal. Now we will go with the conversion. So suppose we are having decimal number system, and this number system we can convert it into either binary or octal or hexadecimal. So there are different methods to convert binary number system into decimal number system into binary, octal and hexadecimal conversion. Okay, so in that case, to convert any decimal number into a base, suppose whatever the base is there, it is having a base, or its base is 2, here the base is 8, and here the base is 16. So suppose we need to convert a decimal number system into any number system that is having a base of r. We need to multiply the fractional part of the decimal number. So at any decimal number that will be represented like suppose 53.45. If this is the number, decimal number, it is a decimal number, and we need to convert it into a number that is having a base r. So what we need to do is we need to divide this part of the decimal with r, and we need to multiply this part with r. So here we need to divide by r, and here we need to multiply by r. So that will give us the equivalent representation of decimal number into the number system that is having a base r. So similarly, we can just proceed further. So if we want to convert decimal number into a binary, the binary is having base 2. So suppose for example, we have taken is 19.25 or 19.125 is the number that is in decimal, that is having a base 10. We need to convert it into a base 2. So if we want to convert it into base 2, that means into binary, what we will be doing is we need to divide this part by 2, and we need to multiply this part by 2. So first on the left part we will just say if it is 19, we will be dividing it by 2, and we will be writing the quotient part here and the remainder part here. So if we are going to divide it, so it will be going for 9 times, it will be 18. So 9 times it is 18, and 1 is the remainder. So whatever the remainder is there, we need to write here. 1 is the remainder. So again we will be dividing it by 2, so it will go for 4, and again the remainder is 1. Again we will be dividing it further, so it will go for 2 times, there is no remainder. Again we will be dividing it, it will go with 1 times. Okay, so once we will be keep on dividing till the quotient that is coming, that will not be further divided by the radix, that is r. So that's 2, so 1 cannot be divided further by 2, so we'll stop here. So now the equivalent representation of 19 into the binary will be this one quotient part, the final quotient part that is left, that is 1, with considering to these values, remainder values. So its equivalent representation of 19 here. So this 19 with base 10 will be represented by 1011. So 1011, that will be in binary. This is only the 19, that is the non-fractional part. So if we have a fractional part also, we need to multiply this fractional part with 2. So fractional part is 0.125. So we will be multiplying it by 2. So 0.125, if we will be multiplying, we get 0.25. So if it is 0.25, then the first binary digit will be this 0. And again, we will be multiplying the remaining fractional part, that is 0.25 with 2 again, and we will be multiplying, it will be 0.50. So the next binary digit will be this, and the remaining fractional part we will be again multiplying. Now it is 1.00. The next one will be this bit. So from there we need to stop when we get the fractional part 0. If we get this, then we will be stopping the multiplication of the fractional part. So now the equivalent representation will be, if it is 0, here 0. If it is 0, again 0. Here is 1, so 1. So equivalent representation will be 0, 0 and 1. So from upside to down we will be representing. So the representation of 0.125 is 10 to equivalent binary will be 0.001. So 0.001 into binary. So by combining both, we can just see 19.125 in decimal will be equivalent to 1011. From there we can get the equivalent representation of 1.25 or 0.125, that is 001. So it will be the equivalent binary representation. We have missed 10 actually when we were dividing. So once on the first time we will be dividing it, so it will be 9 times, remainder is 1, again 4, remainder is 1, 2, remainder is 0, 2, 1. Okay, one missing 0 is because of the remainder. So here when we have divided 2 to 2, it is 1 times it will be going, and it will be having a remainder of 0. Sorry for the mistake. So now this will be the representation, we will be representing it. So here it will be, because once we are dividing we need to consider the remainder, what was the remainder. So once we have divided the 2 by 2, it goes for 1 times, but there was a remainder 0. So we need to consider that 0. If I forgot to write here, okay, so it will be 1 0 0 1 1. Okay, yeah, so that will be the equivalent representation. So it is 10011 point, and this is the fractional part equivalent. Okay, so I hope you have got the point. So a next example we will take for conversion of a decimal to octal number system. So any decimal number system is there, we need to convert it into an octal number system. So again, the same concept we will be using. Like if a base is r, we need to divide this part of decimal number by r and the fractional part by multiplying. Okay, so again, suppose we are having a representation case of octal. To octal we are going to represent, so it is suppose 15.125. suppose this is the number, or again we can take the previous one also. So if this is the number, we need to represent in terms of base 8. So for representing this, we need to multiply here, we need to divide it, so by 8 19. Okay, so by dividing it, whatever the remainder will be there, we will be writing it here. So 8, it will go for 2 times, 8 to the 16. So if it is 16, 3 will be the remainder. Now this 2 will not be further divided by 8, so we will stop here only. Okay, so the representation will be 2 and 3. So 19 in decimal will be represented as 2 3 in octal. So next is 0.125. So this part will be multiplied by 8. This part is divided by 8. So here we will be multiplying it by 8. Once we multiplied it, it will be 1.00 itself. So that will be 1000. Okay. So 1.00 itself. So once it is 00, we will stop here. We need to multiply further, and this representation will be 1. So 0.125 in decimal can be represented by 0.1 in octal. So just by combining, we can get like this will be represented by 19.125 will be represented by 23.1 in case of octal. Next is hexadecimal. So to hexadecimal, we need to take the same example, suppose 125. So similar to that, just go with this. How you will be converting? Just let me know what is the equivalent of 19.125 in decimal to hexadecimal. Just go with the previous step that we have followed. Similar step we will be following here also. Just convert it. So it is 19. We will be doing the division part. So once we will be dividing, it will go for 1 time, and the remainder will be 3. Okay. So the representation will be starting with the quotient part and then going with the remainder part. So it will be 1 3 point. So now 0.125 we will be multiplying with 16. Once we have multiplied by 8, we have got 1. Now we will be multiplying by 16, then it will be 2. So 2.00. So once it is 00, we will be stopping here. So the representation will be 2. So 0.125 will be represented by 2. So it is 13.2 will be the representation in case of hexadecimal. Okay, so we have converted decimal number system into binary, octal, and hexadecimal. Okay, so next we will see is suppose binary. We will be converting binary to different number systems.
Sir,
So decimal, yes,
when we are converting a number from decimal to binary, what if
yeah.
we are not getting zeros?
What if we are not getting 0? Okay, so if it is a fractional part, we are not getting 0. What we will be doing is after calculation of, like suppose you have a number, decimal number. Suppose you have a number, decimal number, that is 10.125937829. Suppose, and 3 and keep on. If this is the number, what we do, we based on our accuracy, like suppose it is, we write it like we need to write up to 3 decimal places. So what we do, we will be writing up to 3 decimal places. If it is for our accuracy, suppose we want just means we need to just truncate to some decimal equivalent. Okay, so it is 10 point. So for 2 decimal places we need to truncate it. So we will be rounding it off to for 2 decimal places. So it is 1 2. Okay, or it is 3. So we will be considering. So for 3 decimal places we need to write. So it will be truncating it to like 1.26. We will not be considering all the remaining decimal digits that are there. So similar in the binary also, if it is we are getting suppose 0 1 0 1 and 1 1 0 1 1 0 and keep on, it is going on. So we will not be writing all the uh, uh, digits. We will be considering a few. Okay, so we will be considering only suppose we up to 3 decimal places or 30 binary places we will be considering. So 3 places after decimal we will be considering. So it's not like we need to keep on multiplying. So we'll be stopping for after doing some iterations. Okay.
Thank you, sir.
Yes. So we will be now converting binary to decimal, then octal, and then again the hexadecimal. So any number is given, that is a binary number. Then with the help of its equivalent representation in terms of decimal, we will be representing it like suppose we are having number that is given to be like 110.11. Suppose this is a binary number, we need to convert it into equivalent decimal. So while converting any number system, either it is octal, hexadecimal, or binary to decimal, then we will be employing the concept of weight. Okay, so here while writing this binary number, each digit is having its weight. Okay, so like after decimal, if we go on the left side, so the first number, this is having a weight of 2 to the power 0. This is having a weight of 2 to the power 1. Whatever the base is there, octal is there. If it is octal, it will be 8 to the power 0, 8 to the power 1, like that. So if it is binary, it will be 2 to the power 0, 2 to the power 1, and this will be having a weight of 2 to the power 2. So it goes positive side. I think it is visible to you or not. Just your understanding, we will be writing it. Yeah. So it is 2 to the power 0, and it will be having a weight of 2 to the power plus 1, and it will be having a weight of 2 to the power plus 2. Similarly, further digits are there, that will be 2 to the power plus 3 and plus 4, like that. On the right hand side, the weights are defined like it will be 2 to the power minus 1. This will be having a weight of 2 to the power minus 2. And similarly, further digits are there, that will be 2 to the power minus 3. Like that, this is the weight of each of the binary digits available in this number. So what we will be doing is, to represent its equivalent decimal number, we will just multiply these weights by their respective digits. So we will be in the on the left hand side. So it is 1. 1 was the number, and we will be multiplying it by the respective weight. So weight is 2 to the power plus 2, plus we will be writing the plus, then plus next number, that is 1, it will be multiplied by the respective weight, that is 2 to the power plus 1. Next is plus 0 is the next weight, next digit. So 0 will be multiplied by the weight, that is 2 to the power 0. Okay. Next is, we will be doing the plus. Now what we will be doing is plus 1. 1 is the digit. It will be having a weight of 2 to the power minus 1. Then again plus, next digit is again 1 multiplied by 2 to the power, that is the weight is having minus 2. We will get the equivalent of this binary into a decimal number system. So it is 1 multiplied by 2 to the power 2, that is 4, plus 1 into 2 to the power 1, that is 2, plus 0 multiplied by something is 0, plus 1 multiplied by 2 to the power minus 1. So it is 1 by 2 plus 1 multiplied by 2 to the power minus 2, that is 1 by minus 2 is on downside, it will be plus 2, so it will be 1 by 4. So we will be writing it 4 plus 2 is 6, plus 1.2 is 0.5, and 1.4 is 0.25. So we will be adding it, so it will be 6 point, if we will be adding it these two, so it will be 5 to 7, so 7 5. So this is 6.75. So its equivalent representation will be 6.75 in decimal. So I hope you have got. So this is the case in case of binary. If it is having binary number system, this will be the case. If it is octal only, then instead of 2 to the power something, we will be writing 8 to the power 0, 1 or 2. This is how we will be converting to decimal. So we will see that next. Okay. So next is, we need to convert into octal. Any number system is there. So to octal, if we want to convert binary to octal, so suppose binary representation is there, and we need to convert it into octal. So to convert it into octal, it is a very simple method to convert this. So what we need to do is, we need to make pairs of 3. So on this decimal, this is a decimal. On the left side of decimal, we will be making the pair of 3 binary digits. So it will be 001, one pair will be there, 100, another pair. So this pair 001, what is its decimal equivalent? Decimal equivalent of 001, what is it? 1. And decimal equivalent of 111, that is 7. Okay. And similarly, we will be making the pair of 3. So now on the right side of decimal, we will be making the pair of 3 digits in case of binary. Okay. So we will be making pair from the starting with the decimal points. Okay. But in case of left side, we have made again from the starting point. So it is 101 will be one pair, and next there is 2 digits, that is 0 and 1. So what we will be making is, to make the pair of 3, we will be extra padding a 0. We will be padding a 0 here. So it will be now 0, 0, 0, 1, 0 will be one pair. So 101 in uh, decimal will be represented by, like 101, it is equivalent to 5, and this is 0, 1, 0, it is equivalent to 2. So now the equivalent octal digit will be 71.52. We will take another example. Suppose if this is the binary, we need to convert it into octal number system. So again, we will be making the pair. So starting with the left side of the decimal, we will be starting from here, one pair. So starting with here, one pair and one pair similarly. Okay, so 3 digits we have made one pair. This is one digit only. So to make the 3-digit pair, we need to add 2 extra digit on the left side. So there will be, whatever zeros we are adding, there will be of no significance. Okay, so we will be adding to make the pair. So again we can make here pair. So there is 001 is equivalent to 1, and again 010 is equivalent to 2. And on the decimal right side of the decimal, we will be making the pair. So this is one pair, 110. So 110 is 6, and this is one remaining. So only one digit is remaining. To make the pair of 3 digit, we will be making 2 extra digit zero padding. So it will be second one 100. So 100 is equivalent to 4. So now its equivalent octal will be 12.64. Okay. So isn't it simple? We just need to make the pair of 3 digits. So here, make pair of 3 digits. Okay, so here we need to make the pair of 3 digits. This is how we can convert an binary into octal. So next one is, we need to convert binary to hexadecimal. So to convert any binary to hexadecimal, we again need to make pair of 4 digits. So in the octal we have made the pair of 3 digits. Now in hexadecimal, we need to convert from binary to hexadecimal. Then we need to make pair of 4 digits. Okay, so suppose this is the number we need to convert into equivalent hexadecimal. We need to convert this by using the 4-digit pairing. So now we will be making the pairing of 4 digits. So starting with here up to here, one digit is there. So it is 101, and there is extra digit required. So we will be making a 0. So now the pairing will be 1010, second pairing. So 0010 is equivalent to 2, and 0 1 0 1, it is equivalent to 5. And again on the left hand side, right hand side of the decimal, we will be making the pairing of four digits. So 0 1 1 1, so it will be one pair, and second pair is 0 0 1, and again one digit is required, so we will be writing a 0. So now the pairing will be 0 0 1 0. So it is 0 1 1 1, that is equivalent to 7, and 0 0 1 0 is equivalent to 2. So its equivalent of hexadecimal is 52.72. Okay, so I hope you have got the point. So next we will see is how we can convert an octal number system to its equivalent decimal, binary, and hexadecimal. So to convert an octal into decimal, again we will use the same concept of weights of the digits. So if there is a digit written is 89.25 in octal, we need to convert it into decimal. So what we will be doing is write its equivalent weight. So at this position the weight will be 8 to the power 0. At this position the weight will be 8 to the power plus 1. At this location the weight will be 8 to the power minus 1, and at this location the weight will be 8 to the power minus 2. So its equivalent we will be writing is 8 multiplied by 8 to the power minus 1, sorry, plus 1, plus 9 multiplied by 8 to the power 0, plus 2 multiplied by 8 to the power minus 1, plus 5 multiplied by 8 to the power minus 2. So whatever its equivalent is coming out to be there, that will be our equivalent decimal. Okay. Next, this is how we can convert from octal to a decimal. Next is we need to convert to binary. If we want to convert to binary and given octal number, suppose a given number is 89.25, we need to convert it into binary. So what we can do is we can represent each digit of octal to its 3-bit binary number. So 8 can be represented in terms of, sorry, one mistake I have done. So first of all, it is 8 is there octal number system. It cannot be 8 and 9. So in octal up to 7 digits are only allowed. Okay, so we have just made a mistake. So it should be, we need to convert it. So all the digits that is possible in octal number system is only up to 7. So it should be, suppose 72 is there, that is valid octal number. So we need to make it 7 multiplied by 8 to the power plus 1, 2 multiplied by 8 to the power 0. Okay, so this will be our equivalent uh, octal to binary conversion, octal to decimal conversion. So next, while converting to binary, we need to represent it also 72.25. So now in octal the digits are ranging between 0 to 7 only. Okay, so we cannot write 8 and 9. So this was a mistake. So now, so it is a 7. So we will be writing this 7 to its equivalent 3-digit number. So it is 7. So it will be represented by 111 into binary. So 2 into binary will be 010. This 2 will be 010, and 5 will be in 3 decimal binary representation. It will be 101. So this is how we can represent each of the digit of octal number system. So the similar representation will be the binary. So if we want to convert it into binary, it will be 111, then 010.010, then 101. So each digit of octal can be represented by its 3-digit binary representation that will give you the binary representation of the octal number system. Okay, this is how we can convert it into binary. Similarly, if we want to convert it into hexadecimal, so for hexadecimal, so if we want to convert it into hexadecimal, we need to first convert it into binary, and then by binary we can convert into the hexadecimal. But for that, we need to go through the binary mode. So once we have converted it into binary, we will be representing this binary like the above we have seen already 111.010.010.101. This was the binary representation of the above number. If we want to convert it into hexadecimal, instead of making pair of 3, now we will be making this we have already done, like how we can convert from binary to hexadecimal. We will make the pair of 4. So again this is 2, so 2 will be extra padding 1 pair. 1, 2, 3, 4. The 2 digits are remaining, so will be extra padding. So this 0011, that is 3. Next is 1010, that is 8 plus 2, that is 10. 10 is represented by A in hexadecimal, that is 16. That is 0101, that is 5. 0100, that is 4. So its equivalent will be 3A.54. This is its hexadecimal equivalent. So similarly is the hexadecimal conversion. So if hexadecimal number is there, we can convert it into decimal, binary, and octal. So in decimal, we will be using the concept of weight. Equivalent weights we have already given. So it is suppose A 2.3B. If this is the number, we need to convert it into decimal. So equivalent weight will be multiplying. So here the weight will be 16 to the power 0. So this is 16 to the power plus 1. Here the weight will be 16 to the power minus 1. Here the weight will be 16 to the power minus 2. So by multiplying the respective weights and adding, we will be getting the decimal equivalent. Similarly, in case of binary, if it is A 2.3B, in binary we need to convert. So we will be writing its equivalent binary in 4 digits of binary. So A, that is 10, so it will be 0, 1, 0, 1, 0 in 4 bit, 2 in 4 bit. So 0, 0, 1, 0, 3 in 4 bit, 0, 1, 0, 0, 1, 1. B, that is 11, so 11 will be represented as 8, 10, 11. So the equivalent binary representation will be 101000.00111011. This will be its equivalent binary. So once we know the equivalent binary, we need to convert it into octal. So to convert it into octal, we need to proceed by, if we want to convert it into octal, we need to proceed by conversion to binary and then proceeding to octal. So we have already converted into the binary, so we will be making the pair of 3. So if extra 0 is required, we will be making the pair. So it is 0, 1, 0, it is 2, this is 4, this is 2. And we will be making the pair here 1, 6, 6. So its equivalent octal will be 242.166 into octal. This is how we can convert each of the different number system into their respective number systems.